And welcome to my talk on jigsaw puzzle solving with Python using computer vision techniques. And as we know, computer vision is all about understanding and processing images using computer systems and techniques. And the relevance or applications of CV algorithms are present in virtually every aspect of our daily life. And because the majority of information we encounter each day is majorly visual information. And this marks the study of CV algorithms in Python environment critically important. And today I will talk about, in particular, how to use CV algorithms in an archaeological and research context. And traditionally using CV algorithms for academic research, and especially humanity research, is kind of a niche area of expertise because the majority of CV applications are profit-driven and non-humanities related. But in recent years, especially with the trends like AI for science and digital humanity research are becoming more relevant, this kind of research is also becoming much more important. So before we talk about algorithms, a few words of self-introduction. So I'm currently a PhD student at University of Cambridge at the Faculty of Asian and Middle Eastern Studies. I major in archaeology, paleography, and manuscript studies. So this involves a variety of different script systems, and in particular the fascinating inscriptions written on turtle shells and ox shoulder blades from ancient China. So my PhD thesis focuses on the Orgobone artifact collection, as it is called, housed at the Cambridge University Library. So I'm the first ever PhD student that works on this collection because the collection is so rare and it contains inscriptions from 3,000 years ago. And the majority of it are fragments, so they are not complete. So that's the need for reconstructing these images based on image processing, kind of like doing jigsaw puzzles, but on the archaic fragments. So you can imagine it's an infinitely fascinating topic because it has relevance for 3D modeling in regard of pottery shards and statues, because we have 3D models and we use 3D related time series analysis for reconstructing these different fragments and materials. And in my lecture, I'm also a computer science enthusiast, and we do research like OCR and image repair primarily through super resolution tasks, and also we do image comprehension. And because in recent years, LL models are becoming quite popular, and it would be fantastic to apply this in Asian scripts, where the LL models can comprehend what is in the images based on the input and prompts. And also, I work as an amateur full-stack web developer. So to make my research ideas into softwares, for wider public benefit, I created an academic website called the Ocular Digital website. You can scan the QR code here to see what the website looks like in an academic context. So primarily, I use this website to launch a high-resolution archaic font and also a database for archaic character queries. There are also a lot of modules on image viewer function and various data visualization modules. And in case you are curious how the website is constructed, I use a mixture of JavaScript and Vue.js together with Django framework. And this is not to belittle any other frameworks like React or Angular, but speaking from an individual developer who has very limited time for investing in web development, this combination of techniques I find to be most efficient for creating more simplistic web applications that has high performance. So a few words of introduction on Oracle bones, and especially why this necessitates the development of jigsaw puzzle solving techniques. Because oracle bones they are quite rare, but they are also lesser known compared to Egyptian hieroglyphics and Mesopotamian tablets. The oracle bones are primarily found in the late Shang China from 3,000 years ago. They were primarily used as divination mediums on which the oracles will inscribe and predict important state matters based on the formations of cracks. So in order for inducing these cracks, they drill a series of hollows into the backside and apply intense heating to the backside. So this way the cracks will form on the front. This kind of practice is usually named as scapulomancy or pyromancy because it's related to fire and the divination using animal shoulder blades. And this here is an example of turtle shell fragment. Turtle shells are used because they were believed to possess a spiritual potency that was needed to contact the ancestral spirits and the natural spirits. And this here is a more complete fragment. There are very fewer areas that are missing. And this is also a tracing on what the artifact looks like. So what kind of traces are on them and what kind of inscriptions are written. However, in working in archaeology, we don't always have such luxury of working with high quality data sets or complete fragments. Because in the beginning, these fragments were excavated illegally, so they are unregulated. And because of this, there are a lot of fragmented pieces that were excavated. And as archaeologists, we often have to work with these fragmented pieces. And this is an example of the collection at Cambridge. And the thing with different collections in the world, you never know what one fragment from one particular collection is joined to in another collection. So perhaps this one fragment in this collection are joined with the Carnegie Museum in America. And we simply have very few traditional means for piecing them together because you can imagine there is an astronomical number of pieces. And in order to reconstruct them, you have to work for years and years. And this pit on the right contains 10,000 pieces within one single excavation pit. And the reconstruction need for ancient fragments lie not only in oracle bones, but in other kind of manuscripts and artifacts. So this makes AI for science or AI for archaeology is critically important. So this brings us how to reconstruct different fragments using Python in an archaeological context. And this was typically compared to a jigsaw puzzle solving because you have to piece together different pieces on basis of paleographical features or typological features or based on edges. Sometimes scholars have such luck of piecing different fragments together based on inscriptions. So if you can reconstruct characters based on the continuity and the unity of different scattered texts, you have a higher chance for piecing together different collections. However, if you look at the fragments on the right, between the C and D fragment, there is no other information other than the information on the edges. So you can say contours or edges of an item is the only reliable feature on basis on which we can do Python applications in. So this questions brings forth the consideration of how do we compute the similarity between two fragments and how do we select different parts or contours to compare. So if you look at these different examples, they resemble jigsaw puzzle solving, except they are not uniform. Because remember, a jigsaw solving, they usually involve 4 different edges. But with oracle bones or other manuscripts, the shape is non-uniform. So we don't know how this will turn into, and we don't know which part of the edges begin or end in order to reconstruct 2 different pieces. And on top of that, we have several algorithmic considerations. So the first and foremost is a pure number of calculations needed, because given a data set of n pieces, you have this number of n to the power of 2 combinations, because you don't know which 2 are compatible, and you have to do a piecewise permutations through all of them. So for example, if there are 10,000 pieces, at least 50 million piecewise comparisons are needed to search for relevant candidates. And if we are dealing with larger data sets, the number of calculations needed also rise very quickly, up to 11 billion calculations. And if we attempt to reconstruct different fragments based on deep learning methods, so we can train AI models to compute the similarity between 2 images. And that can be efficient and versatile. However, as we know, the inference of AI models can be very slow. Even if you possess a very high-end graphics card, and it may take 1 second or 2 seconds to compute each comparison. And this creates a lot of a computing power problem, because as individual developers, we don't often have access to CPU clusters or GPU cards. So this means in order to build such a model, the primary concern is to optimize your algorithms. So, and another challenge is the lack of contour data, because as historians, we often deal with images, pure images in PNG formats. So there are no coordinates on their edges. So we need to do a pre-computed contour extraction from images. And also there are also difficulties I mentioned in partitioning different parts of contours, because you don't know what is the starting point and what is the end point. And another challenge is we have so few distance measures. So you can consider cosine distance or Euclidean distance, which are very rigid. So there is no room for a relaxed evaluation between 2 time series. So we need to adapt and build upon the LCSS distance, for example, which stands for longest common sequence. And or we can build an adapted version of Euclidean distance measure, because the similarity between 2 time series should be flexible, and this gives us some ability over control for searching for candidates. So I will be briefly talking about how my model is constructed. And remember, in order to construct a very fast and very reliable computing model, you don't need to rely on very advanced packages or unfamiliar packages, because Python in its native environment possesses a lot of packages that are sufficient enough for meeting our need. So, for example, the most basic, the OpenCV and NumPy can be enough for creating very complex models. We just need to partitioning our entire train of thought into 1 million different steps. And we can do very basic mathematical operations to build a very sophisticated computational model. So first, we need to pre-compute the contours from images. And this is because we need to cut down the computational cost for comparing between 2 images. So instead of comparing 2 images, So why don't we compute between two coordinate arrays, which are basically numbers? Because image-based operations can be very expensive. But if we extract contours from them first, this way we don't have any need for image-related tasks. So in order to achieve this, I believe everyone is very familiar with basic morphological operations or edge detections. So the first thing we need is to read a path from the from a local folder and convert it into grayscale or color images based on your need. And we apply a median blur to the image to prepare for canny edge detection. And once we detect the edges from the images, we draw these contours onto a canvas, and we apply the morphological operation for the object. The reason for that I will touch in a moment. So this is the result for extracting contours from the images. There is only one primary object in our image. And if we look at the result of the code, so once we read the grayscale image into the Python kernel, we can apply morphological operations onto them. And because you can observe there are a lot of gaps between images, so morphological operations such as erosion will close these different gaps and make a very flexible contour extraction from them. And the result of this contour extraction is a 2D coordinate array, only containing XY coordinates. So this way, instead of dealing with images, we are effectively dealing with 2D numbers. So the next question is, how do we compute the similarity between two contours? For example, we can do a very simple Euclidean distance measure to look for discrepancy between edges. So if two edges possess very little Euclidean distance, this means they are very similar. However, the look between contours is that we don't know what is the starting point and what is the end point for measuring. And this sort of task resembles a signal processing task, because once we iterate between each point, so you can observe the change in a 3D space, which the 2D coordinate will change in regard to arc length. So this makes it a 1D signal. And in order to cut down the irrelevant points on this signal, i.e. noise, we need to reduce the noise. We can do some additional filters. For example, the Gaussian filter, which will simplify and smooth the contours around their corners. So for example, a lot of ridges and protrusions on the contours are not relevant. So whether they are there or they are not really relevant to our computations. So we can first apply a Gaussian filter to the contours, and then we can apply a polygon approximation in order to drastically reduce the number of points. There are a lot of algorithms out there, and the most classic one, as we all know, is the Douglas-Pilker algorithm, which simplifies the shape. And this will cut down by almost 19% of points. So originally, there may be 500 points, but once we apply the Gaussian filter and the Douglas-Pilker algorithm, there are only maybe 10 or 20 relevant points. And this is a code that we need in order to achieve this. So once we accept a 2D coordinate array, we can design two separate filters for Gaussian filter and Douglas-Pilker filter. And we adopt essentially a coarse-to-fine strategy for filtering this more efficiently. And for example, once we achieve very rough approximation of the shape, we have this cosine similarity analysis that can be used to compare different segments, because we know only edges that possess similar cosine similarity that they can be remotely joined together. So this adopts a very fast filter in order to search for candidates. And oftentimes, once we translate and rotate based on the similar edges or based on anchors, as I name it, because anchors are located on the ends of the edges. And sometimes that's not enough, because sometimes, like these fragments, they are not joined on the beginning point of the anchors. They need to slide. So we need to perform additional translations and evaluate at each single step. And because we filter this very efficiently, there is only a couple of times that we need to do this. And that's the efficiency and validity of such operations. So once we translate based on similar cosine similarity, we transform the two images close to each other and see whether these two segments have a higher chance of not colliding, but combine very closely. So at each step, when we evaluate, we can first do a collision test, which does not involve any distance measures. This can be done very fast. So if two contours collide by a very high degree, this means they are not compatible in order for fragment reconstruction. But if they deviate too much, this also means the edges are not very similar. So we need to do some kind of rotation corrections at each step and evaluate. So this is the result of the model. So you can see, based on cosine similarities, that there are different positions that we can do. And because of the collision test and the distance measures, we have filtered out a great number of invalid candidates. So this leaves only one question: how do we evaluate and filter based on the results? So what constitutes a best result? So on that, we have a lot of distance measuring algorithms, such as Euclidean and LCSS measure. And the problem is such measures are so rigid. So it's an either-or problem. So they either fit or doesn't fit. So instead, we need to do a weighted sequence of such algorithms, which can apply a sort of a soft measure. For example, as these three different positions, obviously the second and third position will fit better because two fragments are approaching each other more closely. But how do we evaluate? Because LCSS only allows for very short distance similarity. So, but if you look at the second image, obviously when you are sliding the anchors, they are approaching the best position possible very quickly. So we need to also account for this semi-close or semi-far distance using a soft distance measure. And the result of such models can be very efficient. As you can see, in almost every result, the contours are joined to each other based on the longest common sequence. So the one that share the most contour similarity constitutes a best result. And this is also another batch of results that I found using different random fragments. As you can see, they are very close to what human experts can achieve, but using computer models. And one last point to additionally increase the speed for computation is that Python has some kind of limitations in some simple operations compared to C++ or C environment. However, if we write these operations in C++, they can be improved significantly. And some examples for defining functions in C language is to port these functions via py band 11. So we can define functions in C language and export them as native functions that can be imported in Python. So the first thing we do is to write a docstring-like definitions for different functions to be exported. And then we write a setup py in the folder structure and compile it. And once we written this C++ file named measure CPP, and we can import them in Python. And the result of such models combining the algorithmic efficiency and the C++ power, and that we can compute these controls very efficiently in under 50 milliseconds. So this is pretty fast because we are doing a lot of operations, filters, and multi-scale optimizations. So this is my thoughts on how to build a very fast model on jigsaw puzzle solving, but in an academic context. And I welcome any questions on this topic. Thank you.
Thank you, Peichao, for this amazing presentation. I would never expected to see archaeology at PyCon, but I was really surprised. I have a question, and it is, so how many pieces of archaeological puzzles do you have, and did you manage to find any matches with this Python algorithm?
Yeah, the answer for that is we currently have 150,000 fragments in this oracle-bone material alone. And as for other materials such as pottery shards, they also number in millions. And whether I have used this model to reconstruct some new pieces, the answer is no for the moment, because the model is fairly recent, and I have some difficulties in making this into software, because just plotting these figures in Python can be extremely difficult and repetitive, because Python does not offer a native interface for testing these results. So we have to develop our own software for that.
All right. Does anybody else have any other questions?
Thanks for the presentation. You illustrated how to match a couple of pieces. And how do you extend this with the full jigsaw with many pieces? You compare continuously couple of pieces. How do you extend this to the full, maybe say 1,000 pieces?
Yeah. So the major challenge is the wider pliability for irregular data sets. But as the model has demonstrated, it's not limited to this kind of material alone, but any kind of images that contain a primary object that are in irregular shape. So once we extract contours in an XY coordinates, so whether it's oracle bones in archaeological context or it's jigsaw puzzles, but just not in rectangular formats, they also apply in this application of models. Thank you.
All right, one more question.
Hi, thank you for your greatest presentation. Have you ever considered also looking at what's inside each piece to reconstruct the characters inside and also recognize the quality of the match between two pieces?
Yes, thank you for your question. That's a very good one, because obviously, as I said, although the edge is the only reliable feature based on which we can reconstruct, but however, for some fragments, the characters on the fragments can act as an additional clue for rejoining or reconstruction. And this way, we need to adopt a wider framework, not only that we take into account the scores of this model, but also we need to reconstruct NLP models or AI models for testing the continuity between characters or layouts. Because essentially we are dealing with characters on images, so they're not characters in a database. So they're not Unicode characters, but they are images. So we need to deal with it directly and using maybe LL models for each fragment individually. This way we cut down the computation for edge comparisons, but in the meanwhile, we increase the versatility for multifaceted matching strategies. Yeah, thank you.
All right, one last question.
Thank you for the talk. Did you ever think of using the text not for the content but for the orientation? So if you have characters, they're vertical.
Yep.
So if you have two pieces, you can, instead of checking like on a continuous case, like all the rotation possibles, just like, I guess, 2 or 4 axes?
Yeah, that's a good question. But maybe I didn't clarify that very clearly because all the organones are pre-oriented at the start. However, you touch on a very basic distinction between the reconstruction between statues and portrait shards and inscribed materials. Because with inscribed materials such as tablets or bone fragments, we already know which direction it is facing up. However, for portraits, we only have some kind of patterns on the surface, which are not enough for rotation correction. So that's why some Chinese academics refer to organoid fragment reconstruction as the most difficult jigsaw puzzle solving in the world. But actually, I find the portrait shard reconstruction to be most difficult because there are no character information on them. And we need to consider the time series analysis for a single signal. Because remember, this is an XY coordinate, so it is pre-oriented. But for a time series, rotation has no meaning. Yeah,
Thank you.
Thank you.
All right. Thank you, Peichao. That was amazing.